All right, welcome to this month's next installment of Everything I Forgot from Stats class. Today we're going to be talking about something probably everybody is familiar and well read on is linear regression. This would basically just be a review of what you've been taught previously, and um, we will just go over introduction of what linear regression is and I guess when to use it. Compare it to last month's topic of correlation, and then we'll go into some of the details of a simple linear regression model, and then specifically how to derive the equation, and then go into an example. So fairly short. This topic won't take too long, too much of your time. So, but hopefully you'll get some type of refresher out of it. So basic linear regression is a multivariate regression technique used when the outcome is continuous. Basically gives you a slope of how an expected change between two variable groups. It's a statistical procedure that determines the equation of a straight line that best fits a specific set of data. And it's used to predict the value of a dependent variable based on the value of at least least squares on an independent variable. Explains the impact of changes in an independent variable on a dependent variable. Basically all saying similar things, but you're trying to analyze the expected change in your dependent variable y per unit of x, which is your independent variable. So like I said, x is your independent or your explanatory variable, the variable you wish to predict or explain. And y is your dependent variable, your response variable, that's used to predict or explain the dependent variable. So with correlation versus regression, scatter plot can be used to show the relationship between two variables. That's usually the starting point when you have a set of two groups of data. You want to try to compare the two groups and see any relation between them. You typically use a scatter plot, like we saw previously, but correlation analysis is used to measure the strength of the association between two variables. Correlation is only concerned with the strength of the relationship, not the causal effect. No causal effect is implied with correlation. So that's when regression comes in the picture. We use regression instead of correlation when the distribution of x is fixed by the researcher, i.e. the set number of each level of x. We're trying to study the functional dependency between x and y. So just some sample scatter plot graphs showing some linear relationships and curvilinear relationships between x and y. You can see here, just depending on how close the data points are to your best fit line or your model line equation, you can either have strong or weak relationships depending on that. But in order to obtain that model, you have to go through this number of steps. But you can see here, like I said, the more the data sets correlate to the predicted model, the more the relationship can be described as having a more either positive or negative relationships. So in looking at a simple linear regression model, only one independent variable, it's x, and then you're trying to determine the relationship between x and y as described by a linear function. So changes in y are assumed to be related to changes in x. So if we look at the mathematical model for a simple linear regression, this is a basic model where you have y as a dependent variable, and you have this beta 0 as your population y-intercept, and your population slope coefficient is beta 1, and then your independent variable x here. Those all make up the linear component of the regression model. And then you have a random error term here at epsilon, which will help estimate particular data points is seen here in this graphical example of this simple linear regression model. You can see here this epsilon is the random error for this particular value of x. But then the actual line itself is modeled by the y equals beta 0 plus beta 1 x. So the slope here, obviously, like we said, is beta 1, intercept here, beta 0, and then your predicted versus your observed values. So when we go into a simple linear regression equation, you take out that the error value, and you're trying to just determine the actual equation for that particular line that tries to model the relationship between x and y. So the simple linear regression equation provides the best estimates of the population regression line based on your data set. So in this case, y hat here is your estimated or predicted y value for observation I. And then B is the same equation here. B0 is your estimate of the regression intercept. And then B1 is your estimate of the regression slope. And then X obviously is the value for your particular observation I. So B0 and B1 are determined from your data set based on the least squares method. They're basically obtained by finding the values that minimize the sum of the square differences between y and y, your predicted value of y and your actual value of y. So I'm not going to go through the equation itself, but this is here, but software computes this very quickly, so you don't have to do it by hand. So when we interpret the slope and the intercept, B0 is the estimated mean value of y when the value of x is 0. That gives you the starting point of your linear equation. And B1 is the estimate change in the mean value of y as a result of 1 unit increase in x. So the slope of the line, basically. So we're going to go through and walk through an example very briefly and show you just some of the details that are involved with the simple linear regression. In keeping with current events, we want to examine the relationship between the value of the Russian ruble and the number of US imposed sanctions on Russia. So I took some random data that saw online yearly, basically the value of the ruble, the dependent variable here, y, which is the value of the ruble per $1,000 of 1,000 US dollars, and the independent variable, which is the total number of US imposed sanctions. So I took some random values from each of those years, each of the previous years since 2012, and estimated the number of US sanctions here, and this is the data set that we came up with. So once we do the simple scatter plots, you can see there's a downward trend. This is actually an upward trend because the value goes up per 1,000. It shouldn't really be the value, it should be the exchange rate per 1,000 US dollars. But I inverted the x-axis here just to show the effect of the value going down per number of US sanctions. So I use Excel just to do this simple linear regression example. I'm not going to flip back and forth between the two because it's pretty straightforward, but I've captured some screenshots just to tell you exactly how to go back and do it. And so first of all, you need the data analysis package, which Luke, I think, went over previously. This needs to be plugged in before you are able to do this. But you choose data in the data tab, and then you choose data analysis at the plugin, and then you just click the simple regression tool from this package. So then you just select your data, your input data, your Y range and your X range. If you want to include your labels within your analysis, select labels, but make sure they're in the X and Y range, and then you just click OK. And then it outputs this table for you with the summary of all this regression statistics for your particular set of data. So just to highlight here, the coefficients of the intercept, that's your B0, and then your number of sanctions here, your 7.3 is your slope of your line. So this is your basic regression equation here. The value of the ruble and versus equals to the y-intercept plus your slope times the number of US sanctions. So when we add this to the scatter plot, you see this line is representative of this equation. The intercept here is extrapolated out here, and the slope of the line is 70.3. Again, the axis is inverted, so it is actually a positive slope, but just because I inverted it looks negative. So the interpretation of the slope itself, so B0 is the estimated mean of the y when the value of x is 0. If x is 0 in the range of the observed x value. So in our case, there's no x equals 0, so that's not within our range. So we can't accurately predict the value when x equals 0, but that's what the intercept would be in this case. So, but interpreting the slope itself, B1 estimates the change in the mean of y as the result of 1 unit increase in x. So here we have B1 equals 70.3. That basically tells us that the mean exchange rate of the ruble increases by 70.3 for every 1,000 US dollars per US sanction imposed. So if we wanted to make a prediction on the value of the ruble, if there's only 300 sanctions, you can just basically plug into that same equation that you've extrapolated, and it'll give you your prediction based on the model that you've created from your data set. So in this case, if you want to predict the prediction of the ruble value for 300 sanctions, it would be equal to 46,743. So basically, in conclusive terms, you can say the predicted value of the ruble when there are 300 US sanctions is $46,743, or sorry, it should be dollars, rubles per $1,000. So when you're making predictions, like I tried to allude to earlier, when the regression model is for prediction you can only predict within the relevant range of data. So like I said, these extrapolated terms, you can't really extrapolate between the range of observed x, because then it's not really representative of your model, because it's uncertain on how the dependency works outside of the model range. But some assumptions of regression, here's the acronym line. It has to be, it's going to be linear, obviously. Linearity, the relationship between x and y is linear. Independence of errors. The error values are statistically independent, particularly important when data is collected over a period of time. And the normality of error. Error values are normally distributed for any given value of x. And equal variance, the probability distribution of the errors has constant variance. So all these are assumed while you're doing a linear regression model. So if we look deeper into some of the results that are created from the Excel regression output, so there's some inferences about the slope that you can verify with the t-tests. With t-tests for a population slope, you can determine if there is a linear relationship between x and y. So the basic t-test hypothesis, if there's no linear relationship, then the null hypothesis will equal 0. But if there is a linear relationship that does exist, then it will not equal 0. So you look at the t statistic, which is equal to the regression slope coefficient minus the hypothesized slope over the standard error of the slope. And then degrees of freedoms is n of -2. These are all populated once you do your regression analysis in Excel. So the regression equation here, the slope is obviously 70.3. Here, this B1, and then your standard error is calculated here within that table, 7.06, and your t statistic, which is 9.949. So this basically tells you that there is a relationship between the number of U.S. sanctions and the value of rupee, just to further solidify that your model has some meaning. And if we look more closely at the t-test itself, so like we said, the output was, the t-statistic output was 9.949, and that falls outside of the range. If you look up on the t-table, the t-test table, for a degree of freedom of 9, which is here for 0.05 significance value. So the t-statistic of 9.9 is way outside of this range. So the decision here is to reject the null hypothesis, and the p-value is much less than the alpha value that was designated. So there's significant evidence that U.S. sanctions affect the value of the Russian ruble based on this t-test. And then if you look at the additional data there, there's a confidence intervals estimate of the slope. This gives you even more, I guess, data that you can present here. And you can say that we are 95% confident that the average impact of the ruble exchange rate is between 54, the lower 95 percentile, 54.32, and the upper 95 percentile, 86.29 for every 1,000 US dollar per US sanction. So this 95% confidence interval does not include zero. So there's a significant relationship between, sorry, this is a typo here, between the price of the ruble and the number of US sanctions at the 0.05 level of significance. So the last thing to look at in the output of the Excel regression data is your F-test. Basically, it gives you the overall significance in regression and whether or not your linear regression model provides a better fit to the data than a model with no predictor values. So basically, it just shows you how accurate your model is based compared to a model without predictors. So in this case, it populates 1 and 9 degrees of freedom. And the formula for the F statistic is the mean square due to regression over the mean square due to error. And it outputs this as your F statistic here, which is 98.97, and your p-value here, which is significantly less than 0.05. So looking at that for the F-test for significance, you can see here that if you look in the F-test or the F table at a 0.05 significance with degrees of freedoms of 1 and 9, the threshold value is 5.12, and in our F statistics in this case is 98.97, so it's way off of this range. So in this case, you can reject the null hypothesis at an alpha of 0.05, and you can sufficiently say that there's sufficient evidence that the U.S. sanction affect the value of the Russian ruble. And that's pretty much it for this. It's pretty simple. I know everybody's seen linear regression in your past, even if you haven't taken a specific data course. But I'll leave you with this, what's inspired, I guess, the example for this current event. So, and that's pretty much it.
thanks for